Hello and welcome to our fifth video. My name is Tayyib Abu Yaman. We'll be talking about the only odd linear function, which is f of x equal to x. To do so, we identify the x-axis where x is the independent variable and the y-axis where y is the dependent variable. We also identify the line that represents f of x equal to x, which is the only odd linear function. F of x equal to x has a slope equal to 1. So this is f of x equal to x. And we also identified the normal line, which is perpendicular to the f of x equal to x with a slope equal to -1. Now our task is to go ahead and identify the characteristics of f of x equal to x and make some remarks. So let's go ahead and start with the first characteristic. F of x equal to x, we can model it as input process output using the abstraction x feeding a process, and then the output is x, same as the input. And we can map this to what we use in calculus, domain feeding a function, and in return the function will map to the range. So whatever the function received from the domain will be mapped to the range. And that is what we mean over here. F of x equal to x maps every x in its domain to x in its range. Let's take a look at what the domain is. The domain of f of x equal to x is a set of real numbers R. F of x equal to x, where x, the input to the function, is coming from the x-axis, and we know the x-axis represent all the real numbers, positive or negative. So since the input to f is coming from the x-axis, then the domain of the function represents the real numbers. Since f of x equal to x, where x represents any of the real numbers in the x-axis, it's equal to an x. But if x is equal to x, that means every real number in the x-axis has a matching real number into the y-axis. If that is the case, then the y-axis will also represent the real numbers, the set of real numbers. So in that case, we can say f of x equal to x is the set of real numbers R. The domain of f of x equal to x is a set of real numbers R, and so is the range. Let's go to the next characteristic. Says the function f of x has two properties. It is 1-to-1 and it's onto. So the function is 1-to-1 as onto. Let's go ahead and do the mapping. These are just representatives of the x-axis, which is a domain, and these are representative of the y-axis, which are the range. But then we chose the same representatives because f of x equals to x, so we have to choose the same representative. That means both of the domain and the range will have the same number of elements. So let's take a look at the map. If we look at the map, we will see that 3 is mapped by the function to 3, 2 from the domain map the function by 2, and so on. We see the mapping is unique. Every unique element from the domain is mapped to a unique element from the range, and that's what we mean by 1-to-1. And since every element in the domain is mapped to a unique element in the range, then every element in the range is covered by an element from the domain. That means the fact that the range is covered, all the elements are mapped to, that's what's known as onto. Onto means every element in the range is covered by the function mapping. So in that case, this characteristics is clear. We'll go to the next one. For every x in the domain, we have the function f of x is equal to x. We can rewrite this function as f of x equal to 1 times x plus 0. But also f of x equal to 1 times x plus 0 is a linear function representing f of x equal to x is equal actually to f of x equal to x. So this is a linear function, and this is a general formula for the linear function. If we look at the x factor here is m, the x factor here is 1. And if we look at the general formula, it has a constant added to the x component, and we have here 0 added to the x component. That means b must be equal to 0 and m must be equal to 1 for this general formula to be applicable to this function. And it has to be applicable because this function is linear. So once again, characteristic number 4, for every x in the domain, f of x equal to x, which is representation as f of x equal to 1 times x plus 0, and the general formula for linear functions, f of x equal to mx plus b, imply m is equal to 1 and imply b is equal to 0. That is the fourth. So let's go to the fifth characteristic. F of x is an odd function since f of x equal to x implies minus f of x equal to minus x. It's just we have minus before the left term and minus before the right term. So that's what we end up with. And then the next equality, we can just reduce it from here. We're saying f of minus x equal to minus x. So if we look at f of minus 1 equal to minus 1, f of minus 2 equal to minus 2, f of minus x equal to minus x, f of anything is equal to that thing. That thing is positive, it will be positive. That thing is negative, it will be negative. So f of minus x is equal to minus x. So this equation, f of minus x equal to minus x, and this equation, which is just the negative of the original equation, minus f of x equal to minus x. If we look at these two, we see that the right hand side of each of the two equalities is the same, minus x minus x. So if the right hand sides are the same, then the left hand sides must be equal. So the left hand sides must be equal, and this is what we're implying, f of minus x equal to minus f of x. And this is the condition for a function to be odd. If a function satisfies this, then the function is odd. So that's a proof that f of x equal to x is an odd function. Let's take a look at the next characteristic. For every point x comma y is a function of x. And this is something that y equal to x means y is a function of x. Sometimes people will use f of x for y. So y is a function of x, so y is equal to f of x. And the function f of x is equal to y. F of x is equal to y. So we have f of x on both equalities. So that means whatever they equal are also equal. So this f of x equal to y, this is f of x equal to x, that means x is equal to y. So x is equal to y means what? Means that if I pick any point over here, this point have the same distance from the x-axis as it has from the y-axis. So this point is one unit away from the x-axis, and that is it is y value, and it has 1 unit away from the y-axis, and that is x value. This point have 1 unit away from the x-axis and 1 unit away from the y-axis. Any point that lies in f of x equal to x, if you pick up any point, then that point will be away from the x-axis the same amount that is away from the y-axis. And this is what we mean by equidistant from both axes. Now that we have listed all the characteristics, let's go ahead and make some comments. But before we make any comments, we want to point out at one thing. The point 1, 1, if we consider the normal as a mirror, then 1, 1, if it is the object, then its image will be minus 1 comma minus 1. The distance from the image to the normal is the same as the distance from the object to the normal. The only difference between the object and the image is the following. There is a conversion, and by conversion we mean change of sign. If we go from plus x plus 1, which is the left coordinate, we will go crossing the normal, it will change to minus. And f of 1, which is equal to 1, if we cross, it's also converted to minus 1. So the conversion for the function f of x equal to x, the conversion crossing the normal will be for both coordinates, not just for one coordinate. Because of this fact, the same thing applies if we look at 2, 2, it will be the image of it will be minus 2, minus 2. And both of them will be having the same distance away from the origin. That means the normal bisects the function f of x equal to x, bisects it into equal halves, and that will give them the symmetry. So we can say that the normal divides f of x equal to x into symmetric halves. Now that we have said this, let's go ahead and look at our conclusions. The first conclusion says what? Equidistance from both axes implies f of x equal to x is symmetric about its normal curve f of x equal to minus x. And this is the point that we talked about. Let me just put back the normal, and we can see that the normal, we see that f of x equal to x is symmetric around the normal. F of x equal to x cannot be symmetric around the x-axis, cannot be symmetric around the y-axis, simply because if it is symmetric around the y-axis, it must be perpendicular to the y-axis, but it's not. And if it is symmetric around the x-axis, it must be perpendicular, but it's not. So the only thing that it is symmetric around is its normal. And that's the first point over here. So the first point is clear. Equidistance from both axes implies f of x equal to x is symmetric about its normal, which is f of x equal to minus x. The second point is the reflection of x comma f of x across the normal is minus x comma minus f of x. And we can just look at x as 1, f of x as 1, then it will be, its image is the reflection minus 1, minus 1. So reflection of x comma f of x across the normal is minus x comma minus f of x for every x in the domain. Let's take a look at the third mark. The third remark is b equal to 0 and m equal to 1 imply f of x equal to x has a single y-intercept at y equals 0. And sure enough, this line passing through the origin intercepts the y-axis only at the origin. It cannot intercept y-axis anywhere because then it will not be a function. So since it is a straight line, the only intercept is at y equals 0, and it's also at x equals 0. The next point is f of x equal to x is the only odd linear function. This is very important result, or this is very important observation. Maybe somebody have already talked about that one. But anyway, the reason being, if we change the slope. And changing the slope is by changing the angle. If we change the angle of this line, f of x equal to x, if we change it by a fraction of a degree, then most, if not all, these conditions will be violated. So that's why we're saying odd linear functions, there is only one odd linear function, and this is the function that has a slope equal to 1, and it passes through the origin. Let's take a look at the next point. F of x equal to x is not symmetric around the y-axis. We just spoke about it. It cannot be symmetric around the y-axis because it has to be perpendicular to the y-axis to be symmetric around it. Obviously, we're not going to talk about symmetry around the x-axis, because if it is symmetric around the x-axis, it's not a function. So we're not going to talk about that. Now that we have finished our remarks and characteristics, we will just go ahead and say that our next video will be about functions that are neither even nor odd. That's it for our video. Thank you for watching. You have a good day.